Why is light impossibly slow? Tonight, we're going to explore one of the most mind-bending paradoxes in physics. You've probably heard that light is the fastest thing in the universe, traveling at 300,000 kilometers per second. But here's what most people don't realize. Even at this ultimate speed limit, the universe is so unimaginably vast that light itself becomes tragically, almost comically slow. By the end of this journey, you're going to understand exactly why even traveling at the speed of light, a human lifetime becomes completely meaningless on cosmic scales. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. Let's begin. You've probably heard that light is the fastest thing in the universe, traveling at 186,282 miles per second. But here's what most people don't realize. Even at this ultimate speed limit, the universe is so unimaginably vast that light itself becomes tragically, almost comically slow. By the end of this journey, you're going to understand exactly why even traveling at the speed of light, a human lifetime becomes completely meaningless on cosmic scales. Think about that number for a moment. 186,282 miles every single second. The light from your phone screen, the glow from your lamp, the sunlight streaming through your window, all of it racing at this incomprehensible velocity. It's a speed so fast that your mind simply can't process it in any meaningful way. Your brain didn't evolve to understand numbers like this, but let me help you visualize what this actually means. The speed of light in a vacuum is exactly 186,282, 397 miles per second. Not approximately, exactly. This represents the absolute maximum universal speed limit. No object with mass can reach or exceed this value according to Einstein's special relativity. It's not just fast, it's the fastest anything can possibly be. To put this in perspective, light completes more than 7 full trips around Earth's equator in just 1 second. Earth's circumference measures about 24,901 miles, a distance that light covers in roughly 133 seconds. In that same single second, light could circle our entire planet 748 times. Picture that. While you blink, a process that takes about 300 milliseconds, light has already raced around the Earth twice. This speed wasn't discovered yesterday. In 1676, Danish astronomer ʻOumuamua became the first person to measure light's velocity by observing delays in the eclipses of Io, one of Jupiter's moons. His calculation was remarkably close, about 190,156 miles per second. Not bad for the 17th century. By 1983, scientists had refined this measurement using modern lasers, establishing the exact value we use today. They were so confident in this measurement that they actually redefined the meter itself. It's now officially the distance light travels in 1,299,792,558th of a second. But here's the thing that's going to shatter your intuitions about cosmic exploration. This ultimate speed, faster than anything with mass can possibly travel, is impossibly, almost laughably slow when confronted with the true scale of the universe. Let's start with something achievable. NASA's Parker Solar Probe, humanity's fastest spacecraft, reached about 430,000 miles per hour in December 2024. Sounds impressive, right? That's blazing fast by human standards. It's only 0.64% of light speed. The Voyager 1 probe, launched way back in 1977, crawls along at about 38,000 miles per hour. At that speed, it would take over 73,000 years to reach Proxima Centauri, our nearest stellar neighbor. Currently, Voyager 1 sits about 15.5 billion miles from Earth. To give you a sense of that distance, in November 2026, it will reach what astronomers call 1 light day from Earth, meaning its position will be where light from our planet was exactly 24 hours ago. This will be a historic milestone, the first human-made object to reach that distance, and yet in cosmic terms, it's barely left the front porch. Now, let's imagine the impossible. Suppose, hypothetically, that a human being could somehow travel at light speed without the inconvenient reality of being instantly vaporized. Transporting any object with mass to light speed would require practically infinite energy. Einstein's equations tell us that as you approach light speed, your relativistic mass increases exponentially. A single kilogram, about the weight of a textbook, would need energy equivalent to billions of nuclear bombs to reach 99% of light speed. Particle accelerators like the Large Hadron Collider can push protons to 99.99991% of light speed, but these particles weigh less than a trillionth of a gram. Beyond the impossible energy requirements, cosmic radiation at relativistic speeds would destroy any biological structure in milliseconds, and ordinary dust particles would become devastating nuclear projectiles. But let's suspend physics for a moment and take this imaginary journey. Earth's equator measures 24,901 miles. At light speed, you'd complete this distance in 133 seconds, allowing for 48 complete orbits in just 1 second of travel. In a single minute, you could circle Earth 448 times. In an hour, that's 26,181 complete orbits around our planet. The Moon sits an average of 238,855 miles from Earth. Light takes 28 seconds to travel there, and a complete round trip would take 56 seconds. Remember those Apollo missions? The conversations between astronauts on the Moon and Mission Control in Houston had that distinctive 6-second delay, a constant reminder of the growing distances we were starting to conquer. Interestingly, the Moon is slowly drifting away from Earth at about 5 inches per year. In 600 million years, it will be so distant that total solar eclipses will become impossible to observe from Earth's surface. Those magnificent moments when day briefly becomes night, when the sun's corona blazes around the Moon's silhouette, future generations will never experience them. Venus, when it's closest to Earth, sits about 23.6 million miles away. Light takes 2 minutes and 6 seconds to cross that orbital distance. Venus rotates so slowly on its axis that a Venusian day lasts 243 Earth days, longer than its own year of 225 Earth days. Imagine a world where a single day lasts longer than an entire year. At its most distant position, when Venus is on the opposite side of the Sun, the distance increases to about 162 million miles, and light takes 14 minutes and 30 seconds to make the journey. Mars varies dramatically in its distance from Earth, between 33.9 million miles at closest approach and 249 million miles at its farthest. At the closest approach, light travels there in 3 minutes. At maximum distance, it takes 22 minutes. Mars hosts Olympus Mons, the largest volcano in the solar system, standing 5 miles high, 3 times taller than Mount Everest, with a base the size of France. NASA's rovers on Mars, like Perseverance, receive commands with an average delay of 14 minutes. Making real-time control impossible and requiring sophisticated semi-autonomous operation. Picture this, a conversation between a human on Earth and another hypothetical person on Mars would have pauses of 28 minutes between question and answer. Imagine asking someone, "How's the weather?" and waiting half an hour to hear them respond with, "It's sunny." The Sun sits exactly 92,955,807 miles from Earth, a distance astronomers define as 1 astronomical unit. The sunlight warming your face right now was emitted 8 minutes and 20 seconds ago. When you look at the Sun, You're literally seeing the past. If it suddenly vanished, we would continue seeing its light for another 8 minutes before darkness arrived. During solar storms, we observe the eruptions a full 8 minutes before their charged particles reach our magnetosphere, allowing crucial hours of advance warning that can protect satellites and power grids. This time delay becomes our early warning system against the sun's violent outbursts. Now we begin to venture into the true depths of the solar system. Jupiter orbits about 484 million miles from the sun. Light travels from Earth to Jupiter in approximately 43 minutes when the planets are in favorable orbital positions. Jupiter hosts the Great Red Spot, an anticyclonic storm larger than Earth itself that has raged for at least 350 years without stopping. The Juno spacecraft, currently orbiting Jupiter, sends data that takes 43 minutes to reach ground control centers on Earth, making real-time operation impossible. Saturn, with its magnificent rings composed of ice and rock, sits about 870 million miles from the Sun. Light takes 80 minutes to cross that empty space. Saturn's rings are only 33 feet thick, despite spanning 175,000 miles in diameter, proportionally thinner than tissue paper. The Cassini-Huygens mission operated for 13 years around Saturn, with each command facing a communication delay of an hour and a half between transmission and orbital execution. Uranus orbits at 1.8 billion miles from the Sun, nearly 20 times the Earth-Sun distance. Light takes an impressive 2 hours and 40 minutes to cross this abyss. Neptune, the officially recognized most distant blue planet, sits at 2.8 billion miles from the Sun. Traveling at light speed, you would take 4 hours and 10 minutes to reach it. Neptune possesses winds of 1,200 miles per hour, the fastest in the solar system, 5 times more intense than Category 5 hurricanes on Earth. These aren't just numbers. They represent a growing realization that even at the universe's speed limit, our solar system becomes a vast, lonely place where communication delays stretch into hours, where real-time interaction becomes impossible, where the very concept of now starts to lose meaning across these enormous distances. And we haven't even left our cosmic neighborhood yet. Pluto, reclassified as a dwarf planet in 2006, orbits at 367 billion miles from the Sun. Light still takes 5 hours and 30 minutes to cross this frozen abyss. The New Horizons probe took 5 Earth years to reach Pluto in 2015, traveling at about 36,000 miles per hour, demonstrating that even our fastest spacecraft are cosmically insignificant. Think about that for a moment. Nearly a decade of continuous travel just to reach what we once considered the edge of our solar system. And even at light speed, the absolute maximum velocity possible in our universe, you'd need more than 5.5 hours of uninterrupted travel to reach this distant, icy world. 5.5 hours. That's longer than most movies. Longer than a cross-country flight, just to reach a world that's still technically part of our local solar family. But Pluto isn't even close to the real edge. The Kuiper Belt, a region of icy objects left over from the solar system's formation, extends from about 30 to 50 astronomical units from the Sun. This is where the solar system starts to thin out dramatically, where planets give way to scattered chunks of ice and rock drifting in the cosmic dark. Arrokoth, visited by New Horizons after its Pluto flyby, sits at 4.1 billion miles from us. These are the frozen remnants of our solar system's formation, chunks of ice and rock that never quite made it into full planets, scattered across billions of miles of mostly empty space. The density of objects here drops precipitously. While the inner solar system is relatively crowded with planets, moons, and asteroids, the Kuiper Belt is a sparse collection of icy wanderers separated by vast gulfs of nothingness. It's as if someone scattered a handful of pebbles across a football field and called it a neighborhood. The true boundary of our solar system lies much farther out. The heliopause, the frontier where the solar wind meets the interstellar medium, sits at approximately 11.2 billion miles from the Sun. This marks where true interstellar space begins, where our Sun's influence finally gives way to the vast emptiness between stars. Voyager 1 crossed this boundary in August 2012, becoming the first human-made object to enter the space between stars, a civilizational milestone without precedent in human history. Voyager 1 carries a golden record with sounds from Earth, including greetings in 55 languages and music by Bach, a message for possible extraterrestrial life. This tiny spacecraft, no bigger than a small car, now drifts through interstellar space as humanity's first ambassador to the cosmos beyond our solar system. It's moving at about 38,000 miles per hour, and it will continue this journey for tens of thousands of years before it even comes close to another star system. Even at light speed, crossing from the Sun to the heliopause would take 16 hours and 40 minutes of continuous journey through progressive spatial emptiness. But even this isn't the complete picture of our solar system's true extent. The solar system, including the hypothetical Oort cloud of distant comets, may extend up to 100,000 astronomical units, about 1/6 light-years in total radius. To put this absurd distance in context, sunlight would take more than a complete year to travel from the Sun's surface to the outer edge of the Oort cloud. A full year of continuous travel at the universe's speed limit just to cross from one end of our solar system to the other. The Oort cloud is a theoretical spherical shell of icy objects that may surround our entire solar system at distances so vast they defy comprehension. These are the sources of long-period comets, those spectacular visitors that appear in our skies perhaps once in a human lifetime, having fallen inward from distances so remote that their orbital periods stretch across millennia. The cloud itself has never been directly observed. It's so far away and its objects so small and dark that our best telescopes can't detect them. We know it exists only because comets keep arriving from its direction. Let me help you grasp what we've established so far. In 1 minute of light-speed travel, you would complete 448 complete Earth orbits. In an hour, that's 26,881 trips around our entire planet. This hypothetical exercise demonstrates that even the absolute maximum universal speed is tragically insignificant when confronted with the true cosmic distances existing beyond our familiar planetary system. Consider this sobering reality. A human living 80 years could at light speed travel only 80 light-years distance, representing merely 0.08% of our galaxy's diameter. During an entire lifetime at maximum speed, you would reach only about 20,000 stars out of 200 billion existing in the Milky Way, an infinitesimal, insignificant fraction. The circumference of the solar system at the heliopause measures approximately 72 billion miles. Light takes about 33 hours to complete one full circuit around this boundary. Traveling from the Sun to Neptune and back at light speed would take 8 hours and 20 minutes, longer than a typical complete human workday. Just think about that. A round trip to Neptune, still well within our solar system, takes longer than your entire day at the office. The density of planets in the solar system decreases drastically after Neptune, with Pluto and Kuiper Belt objects vastly separated by billions of miles of spatial emptiness. The distance between Neptune and the heliopause is greater than the entire distance between the Sun and Neptune, demonstrating how the solar system becomes hollow and empty in its outer periphery. Here's an analogy that might help you visualize our cosmic isolation. If the solar system were reduced to the size of a penny, about 3/4 of an inch across, the nearest star would be located about 1,170 feet away. nearly 2/3 of a mile of empty space between the closest stellar neighbors. This analogy illustrates the fundamental cosmic isolation of our solar system, separated from neighboring stars by abysses of void almost completely devoid of significant matter. Even traveling continuously at light speed for a complete week, you would barely have left the solar system, reaching only the inner hypothetical Oort cloud. A full month at light speed would allow you to reach approximately 5 light-years. Still insufficient to arrive at the nearest star, Proxima Centauri, at 4.22 light-years distance. The vastness of space between stars means that even at maximum universal velocity, interstellar exploration requires timescales superior to complete individual human life. Probes like Voyager will continue traveling for tens of thousands of years before approaching another star, silent messengers of humanity in the interstellar void. The temporal scale necessary for interstellar journeys vastly exceeds not only individual lives, but potentially the durations of entire terrestrial human civilizations throughout known history. The pyramids of Egypt were built 4,500 years ago, and they would need to endure for 16 times longer than they already have before Voyager 1 comes within even remote proximity of another star. Pluto takes 248 Earth years to complete one full orbit around the Sun. Since its discovery in 1930, it still hasn't completed an entire Plutonian year. We discovered this world, reclassified it as a dwarf planet, sent a spacecraft to visit it, and received those incredible close-up images, all during less than half of one Plutonian year. At light speed, you could orbit Pluto at its average distance from the Sun in approximately 11 hours, but that wouldn't make the journey there any faster. The travel time to destinations remains constant at light speed, regardless of how many orbits you could complete upon eventually arriving after years of displacement. The implacable reality is that spatial distances are measured in billions of miles, and even hundreds of thousands of miles per hour are cosmically negligible velocities. Current spacecraft achieve at maximum 1% of light speed, multiplying by 1,000 all the temporal scales already mentioned in this progressive educational hypothetical exercise. If light speed travel to Proxima Centauri takes 4.22 years, then our fastest current technology would require over 4,000 years to make the same journey. The solar system, despite containing 8 major planets and billions of smaller objects, represents only a minuscule fraction of the distance to the nearest known star. The nearest star to our Sun is Proxima Centauri, a red dwarf distant 4.22 light-years, or about 24.9 trillion miles from Earth. Proxima Centauri is a red dwarf so faint that it cannot be seen with the naked eye, despite being our closest stellar neighbor. While you can easily spot Jupiter or Mars in the night sky with nothing but your eyes, our very nearest stellar companion remains invisible without telescopic assistance. 1 light-year equals 5.88 trillion miles, the distance light travels moving without stopping for 365.25 complete Earth days. Traveling at light speed, you would take 4.22 complete years to reach Proxima Centauri, more than 1,540 days of continuous travel. During that hypothetical journey, you would witness 1,540 Earth sunrises if you could observe our planet throughout the interminable impossible voyage. And yet, all of this, our entire solar system with its 8 planets, asteroid belts, countless moons, and trillion comet Oort cloud, represents less than 1/10,000th of the distance to our very nearest stellar neighbor. Voyager 1, at its current speed of about 38,000 miles per hour, would arrive at Proxima Centauri in 73,775 years of space travel. That represents approximately 2,950 human generations, assuming 25 years per generation, making the journey completely humanly unviable on any multi-generational scale. Think about that number for a moment. Nearly 3,000 generations. When Voyager 1 launched in 1977, it carried a golden record with sounds and images from Earth. Greetings in 55 languages, music by Bach and Chuck Berry, recordings of whale songs and crying babies. By the time that spacecraft reaches our nearest stellar neighbor, every human language on that record may have evolved beyond recognition. Every nation that contributed to that message may have risen and fallen multiple times over. The very concept of humanity, as we understand it today, might be unrecognizable. Proxima Centauri is part of the triple Alpha Centauri system, along with Alpha Centauri A and B, brighter and more massive stars that form our closest stellar neighborhood. Alpha Centauri A and B orbit each other at 4.37 light-years distance, only slightly farther than Proxima, creating a complex gravitational dance in our cosmic backyard. The Alpha Centauri system presents what astronomers call the three-body problem, a chaotic gravitational ballet that makes planetary orbits unstable and unpredictable over time. The three stars orbit a common center of mass in a dynamic system of intense, permanent, mutual gravitational interactions. Any planet unfortunate enough to exist in this system would experience wildly varying seasons as the gravitational tugs of three different stars altered its orbit unpredictably. These are our closest stellar neighbors, but even so, they represent abysses of distance completely incomprehensible to ordinary human intuition. The second nearest individual star is Barnard's star, located 596 light-years away, about 34.8 trillion miles of astronomical distance. Traveling at light speed, you would spend almost 6 complete years reaching this solitary red dwarf in deep space. 6 years of continuous travel at the universe's speed limit just to visit our second closest stellar neighbor. Wolf 359, another nearby red dwarf, sits 786 light-years from Earth, adding extra years to our hypothetical journey. Then there's Sirius, the brightest star in Earth's night sky, located 8.6 light-years away, a brilliant binary stellar system. Sirius is actually a binary system with a white dwarf companion, a collapsed star so dense that a teaspoon of its material would weigh about 11,000 pounds. Even though Sirius is easily visible on any clear night, the light hitting your eyes tonight began its journey 8.6 years ago. When you look up at Sirius, you're seeing how it appeared in 2016, literally contemplating stellar history across temporal spatial vastness. The light you're seeing tonight from Sirius started its journey when smartphones were still considered cutting-edge technology, when people were debating whether virtual reality would ever become mainstream, when the first CRISPR gene editing trials were just beginning. That photon of light has been racing through the vacuum of space for nearly a decade just to reach your retina. Epsilon Eridani, a young sun-like star, lies 10.5 light-years away, a distance where scientists actively search for habitable planets. Within a 15 light-year radius of Earth exist approximately 60 catalogued stellar systems, a reasonable density but still representing immense separation. The majority of these nearby stars are red dwarfs, smaller and dimmer than our Sun, the most common stellar type in the Milky Way galaxy. Only about 20% of nearby stars are visible to the naked eye. The remainder stays invisible without powerful modern telescopes. This means that when you look up at the night sky, you're seeing only a tiny fraction of our stellar neighborhood. The vast majority of our closest neighbors remain hidden in darkness. Expand that search radius to 50 light-years, and you'll find about 1,400 stellar systems. A diverse mixture of varied stellar types. This 50 light-year region represents only a minuscule fraction of the Milky Way, a galaxy that extends unimaginably farther beyond our local cosmic neighborhood. Consider some of the brighter stars you can actually see in the night sky. Vega, that brilliant star in the constellation Lyra, sits 25 light-years away. The light you see from Vega tonight began its journey in the year 2000, when Y2K fears dominated headlines and most people had never heard of social media. Arcturus, a luminous orange giant, lies 37 light-years distant. Its light departed Earth in 1988, when the Berlin Wall still divided Germany and the internet existed only in university research labs. Fomalhaut, a young star surrounded by a planetary debris disk, sits 25 light-years from Earth, an active region of planetary formation that astronomers study intensively for clues about how solar systems develop. These stellar distances start to reveal something profoundly unsettling about cosmic exploration. Traveling at light speed for 100 years, you would cover only 0.1% of the total diameter of our entire Milky Way galaxy. This scale begins to reveal that even maximum universal velocity is tragically slow for significant comprehensive galactic exploration. A human living 80 years could, at light speed, travel only 80 light-years, a minuscule distance compared to our galaxy's 100,000 light-year span. That represents merely 0.08% of the galactic diameter, less than 1,000th of our spiral galaxy's total extent. During an entire human lifetime, at maximum speed, you would reach only about 20,000 stars out of 200 billion existing in the Milky Way. 20,000 sounds like a lot until you realize it's 1/10,000,000th of our galaxy's stellar population. You could spend an entire lifetime visiting new stars every day at light speed and still see less than 0.01% of what's out there. Let's venture beyond our immediate stellar neighborhood and examine some of the more distant, but still relatively nearby, objects visible to the naked eye. The Pleiades star cluster sits approximately 444 light-years from Earth, a group of young, hot, brilliant blue stars. The Pleiades contain about 1,000 stars gravitationally bound together, all born from the same molecular cloud about 100 million years ago. They represent a stellar nursery, a group of infant stars still surrounded by wisps of the nebula that gave birth to them. The light you see tonight from the Pleiades departed during the European Renaissance, when Leonardo da Vinci was still painting masterpieces and Michelangelo was sculpting David. When that light began its journey, the printing press was a recent innovation. The Americas were unknown to European explorers, and the concept of heliocentrism was still considered heretical. The Orion Nebula, that giant stellar formation region, lies 1,344 light-years away, visible to the naked eye as a diffuse nebulous patch in Orion's sword. The Orion Nebula contains sufficient material to create 2,000 sun-like stars, a true stellar maternity ward, visible without any optical assistance on clear winter nights. This nebula extends across about 24 light-years, a region where thousands of new stars are currently being born from collapsing gas clouds. Traveling at light speed, you would take 1,344 years to reach Orion, a journey equivalent to the time span from the height of the Roman Empire until today. Every significant event in recorded human history, from the fall of Rome to the rise and fall of the Byzantine Empire, through the Middle Ages, the Renaissance, the Industrial Revolution, 2 world wars, and the space age, represents less time than a light-speed journey to this nearby star-forming region. The Eagle Nebula, famous for the Hubble Space Telescope's Pillars of Creation image, sits 7,000 light-years from Earth. When you contemplate these distances, something profound becomes clear about our place in the cosmic order. Even traveling at the universe's absolute speed limit, we remain trapped in an impossibly small bubble of space and time. The Eagle Nebula, famous for the Hubble Space Telescope's Pillars of Creation image, sits 7,000 light-years from Earth. But here's something that will fundamentally alter how you think about observing the cosmos. Those majestic pillars of creation that we see in photographs were probably destroyed about 6,000 years ago by a nearby supernova. But the light of that destruction hasn't reached us yet. Think about that for a moment. We're looking at towering columns of gas and dust, stellar nurseries where new stars are being born, marveling at their beauty and grandeur, but they may already be gone. Obliterated millennia ago by a stellar explosion so violent it vaporized these massive structures that span several light years. The light showing us their destruction is still racing toward Earth and won't arrive for another 1,000 years or so. This is the universe's ultimate cosmic delay. We're not just seeing the past when we look at distant objects. We're seeing a past that might not even represent current reality. The gas pillars we observe were destroyed thousands of years ago by a supernova, but their light still hasn't reached us due to the cosmic lag imposed by light's finite speed. Imagine watching a movie where the action you're seeing happened 6,000 years before you were born, and the dramatic climax is still en route to your screen. That's what astronomical observation really is, a delayed broadcast from the deep past, where the most important events might already be over before their light reaches our telescopes. The Carina Nebula, home to the unstable hypergiant Eta Carinae, lies 8,500 light-years away, one of the most violent and luminous regions known in our galaxy. Even at light speed, it would take 8,500 years to personally witness the explosions and eruptions of this extreme turbulent region. Eta Carinae is a stellar monster, a star so massive and unstable that astronomers expect it to explode as a hypernova within the next million years. When it does, the explosion will be visible from Earth in broad daylight, outshining Venus, and possibly even rivaling the moon's brightness. But if it exploded right now, this very second as you read these words, we wouldn't know about it until nearly the year 10,500. The Roman Empire would rise and fall, the entire medieval period would pass, the Renaissance would bloom, the Industrial Revolution would transform the world, and we'd colonize Mars, all before we'd see the flash from that explosion. Now let's zoom out even further and examine the structure of our galaxy itself. Our solar system sits in the Orion Arm, a minor spur of the Milky Way, measuring about 3,500 light-years in total width. Crossing just our local spiral arm at light speed would take 3,500 years, a period longer than all documented human civilization. The entire recorded history of human culture, from the earliest Sumerian city-states through the Egyptian dynasties, the rise and fall of Rome, the Middle Ages, the Renaissance, the Industrial Revolution, and into the modern era, all of that represents less time than it would take light to cross just our small section of one galactic arm. Think about that scope for a moment. Every war ever fought, every empire that ever rose and fell, every scientific discovery, every work of art, every human life that has ever been lived, all of human history combined, doesn't add up to the time light needs to cross our local galactic neighborhood. The Perseus Arm, the larger adjacent spiral structure, lies about 6,500 light-years away from our Orion Arm. These are the major architectural features of our galaxy, vast spiral lanes of stars and gas stretching across tens of thousands of light-years, separated by cosmic gulfs that would take millennia to traverse even at the universe's speed limit. If our solar system were a house in a suburban neighborhood, the Perseus Arm would be like the next county over. Except instead of a 30-minute drive, it would be a 6,500-year journey at the fastest possible speed. The distance between galactic spiral arms dwarfs the entire span of human civilization. The galactic center, where the supermassive black hole Sagittarius A resides, sits 26,000 light-years from Earth in the direction of the constellation Sagittarius. Sagittarius A, the central black hole, contains the mass of 4 million suns concentrated in a region smaller than Mercury's orbit, drastically warping space-time around itself. The light we observe today from the galactic center was emitted during the Ice Age, when woolly mammoths still roamed the frozen Earth. When those photons began their journey toward us, humans were just beginning to develop agriculture. Written language didn't exist, and the Great Pyramids were still 20,000 years in the future. The light hitting our telescopes tonight from the galactic center is older than civilization itself. Sagittarius A possesses mass equivalent to 4 million suns, a supermassive black hole gravitationally dominant in the dense galactic nucleus. Traveling at light speed to the galactic center, you would witness 26,000 years of human evolution pass on Earth during your departure. By the time you arrived, humanity might be an entirely different species, or might not exist at all. Consider what 26,000 years represents in terms of human development. When your journey began, humans would still be hunter-gatherers. Agriculture wouldn't be invented for another 14,000 years. The first cities wouldn't arise for 20,000 years. By the time you reach the galactic center, humans might have evolved into something unrecognizable, or they might have engineered themselves into post-biological entities, or they might have gone extinct and been replaced by their artificial creations. The central region contains about 10 million stars densely concentrated within just 1 parsec, about 326 light-years, of the massive central black hole. This is stellar density beyond imagination. While in our local neighborhood stars are separated by light years, near the galactic center, they're packed so tightly that their gravitational interactions create a stellar ballet of incredible complexity. If Earth existed in that environment, our night sky would blaze with thousands of stars brighter than Venus. The Sagittarius Centaurus arm, a major spiral structure, extends from 10,000 to 15,000 light-years from the galactic center in a complex curved configuration. To travel from the galactic center to the opposite edge of the Milky Way would require 50,000 years of uninterrupted journey at maximum universal velocity. The Milky Way has a diameter of approximately 100,000 light-years, measuring the main visible stellar disk filled with bright stars. Some recent studies suggest the disk may extend up to 200,000 light-years, including outer regions of sparse dispersed stars. Crossing the Milky Way from edge to edge at light speed would take 100,000 complete years, a period longer than the existence of Homo sapiens. During such a journey, humanity could evolve into a completely different species or even become extinct through severe planetary environmental changes. The entire span of modern human existence, from our emergence in Africa to the present day, represents the minimum travel time across our own galaxy at the universe's speed limit. The Milky Way contains between 200 and 400 billion stars, according to the most reliable and updated modern astronomical estimates. If each star were represented by a grain of sand, we would need several completely filled Olympic swimming pools to represent them all physically together. If you tried counting them at 1 per second, working 24 hours a day without rest, it would take between 300 and 12,600 years to count all the galactic stars, longer than all of recorded human history just to count our local galactic neighborhood. The total mass of the Milky Way, including invisible dark matter, is estimated between 750 billion and 1 trillion solar masses. Dark matter, which emits no detectable light, comprises about 85% of total galactic mass, remaining mysterious and invisible always. We know it's there only because of its gravitational effects on visible matter, but we've never directly detected a single dark matter particle despite decades of searching. The galactic halo extends up to 2 million light-years, including dark matter, 20 times larger than the main visible stellar disk. Our galaxy isn't just the spiral disk you see in photographs. It's embedded in a vast sphere of dark matter that extends far beyond the visible stars, creating an invisible architecture that we can only detect through its gravitational influence. Our solar system orbits the galactic center at approximately 560,000 miles per hour, an astounding velocity compared to terrestrial human speeds. One galactic year, the period to complete a full orbit, lasts about 225 million Earth years. Immense, unimaginable geological time. Since the Sun's formation 6 billion years ago, it has completed only 20 complete galactic orbits around the dense center. 1 galactic year ago, dinosaurs were beginning their domination of Triassic Earth, while mammals remain minuscule and totally insignificant. 2 galactic years ago, complex multicellular life was just starting to evolve in primordial Precambrian terrestrial oceans. The Milky Way also moves through space at about 1.3 million miles per hour toward the Virgo supercluster, part of complex cosmic motion. Everything in the universe is in constant motion. Nothing remains truly static in dynamic space-time under continuous accelerated expansion. Galactic rotation isn't uniform. Stars at different radii orbit at distinct velocities, a complex pattern maintained by dark matter. Stars in the galactic center complete orbits in just a few million years due to the intense gravity of the central massive black hole. In the galactic periphery, stars take hundreds of millions of years for one complete orbit, demonstrating evident orbital velocity gradients. This is the scale of our local cosmic neighborhood. We haven't even begun to consider what lies beyond our galaxy. The Large Magellanic Cloud, an irregular dwarf satellite galaxy, sits 160,000 light-years from the Milky Way, visible to the naked eye in the southern hemisphere. The Large Magellanic Cloud is being slowly cannibalized by the Milky Way. In 5 billion years, it will be completely absorbed and cease to exist as an independent galaxy. This cosmic cannibalism is happening right now as you read these words. Streams of stars are being gravitationally stripped from the Large Magellanic Cloud and incorporated into our galaxy's structure. It's a slow-motion collision spanning billions of years, a galactic meal that began long before Earth formed and will continue long after our sun dies. Imagine watching a movie where each frame represents 1,000,000 years. That's the timescale of this galactic consumption. The small Magellanic Cloud, the smaller companion, lies at 200,000 light-years, both orbiting our massive main galaxy gravitationally. Traveling at light speed, you would take 160,000 years to reach the Large Magellanic Cloud, a time period longer than the existence of modern Homo sapiens. Think about that timeline. When the light we see tonight from the Large Magellanic Cloud began its journey, modern humans didn't exist. Neanderthals were still hundreds of thousands of years in the future. Our species hadn't even begun to evolve. Every step in human evolution, from our earliest proto-human ancestors to the development of language, art, agriculture, civilization, and space travel, all of it represents less time than light takes to travel from our nearest galactic neighbor. The light reaching your eyes tonight from the Large Magellanic Cloud is older than human consciousness itself. It's older than tools, older than fire, older than any trace of what we might recognize as distinctly human behavior. That photon has been racing through space since before our ancestors descended from the trees. But even these satellite galaxies are practically next-door neighbors compared to what lies beyond. The Andromeda galaxy, M31, our giant spiral neighbor, sits 5 million light-years from Earth, an intergalactic distance so unimaginably vast it defies comprehension. Andromeda contains approximately 1 trillion stars, more than double the Milky Way's population, making it the massive dominant galaxy in our local group. The light we see from Andromeda tonight was emitted 5 million years ago, when primitive human ancestors were just beginning to make stone tools. When those photons began their journey toward Earth, our ancestors were barely distinguishable from other primates. They had no language, no fire, no tools beyond perhaps crude stones. The entire development of human intelligence, culture, and civilization has occurred during the time that light has been traveling from Andromeda to your eyes. Consider the enormity of that statement. Every word ever spoken, every song ever sung, every book ever written, every scientific discovery, every work of art, every moment of love or loss or triumph or tragedy in human history, all of it has happened while that single beam of light crossed the cosmic void between Andromeda and Earth. Traveling at light speed to Andromeda, you would cross the intergalactic abyss for 5 million years, a complete, enormous evolutionary period. During that journey, the human species could emerge, evolve, dominate the planet, develop civilization, and potentially become completely extinct through catastrophic events. The entire story of humanity from beginning to end could unfold multiple times during a single light-speed journey to our nearest major galactic neighbor. Andromeda approaches the Milky Way at about 250,000 miles per hour. Both will collide and merge in approximately 5 billion years. This collision won't destroy individual stars due to the immense distances between them, but will completely reconfigure galactic structures into a new, giant, elliptical galaxy. Astronomers have already dubbed this future merged galaxy Milkomeda. When this cosmic collision occurs, it will be the most spectacular sight ever witnessed by any inhabitants of either galaxy. The night sky will blaze with new star formation as gas clouds collide and compress, triggering stellar nurseries across both galaxies. Gravity will fling stars into new orbits, creating tidal streams of light across the heavens. But don't worry about buying protective gear. This event is so far in the future that our sun will have already exhausted half its nuclear fuel and begun expanding into a red giant. The local group contains about 54 gravitationally bound galaxies, including the Milky Way and Andromeda as the dominant massive members. This group extends approximately 10 million light-years in diameter, a volume containing trillions of stars, collectively grouped gravitationally. The triangular galaxy M33, the third largest member of the local group, sits 273 million light-years away, a comparatively smaller spiral galaxy. Crossing the local group from edge to edge at light speed would take 10 million years, a period longer than the existence of hominids. Here's a mind-bending perspective. When the first hominids evolved 6 million years ago, a photon departing from them still wouldn't have completely traversed the local group. Most galaxies in the local group are dwarfs, containing only millions or billions of stars, minuscule compared to giant spirals like ours and Andromeda. Some dwarf galaxies are being gravitationally torn apart by the Milky Way, their stars assimilated over billions of future years. Stellar streams in the galactic halo are remnants of destroyed dwarf galaxies, archaeological evidence of our galaxy's violent, turbulent past history. Our galaxy is littered with the debris of smaller galaxies it has consumed over billions of years, like a cosmic predator surrounded by the bones of its prey. These stellar streams tell stories of galactic violence that dwarf any terrestrial catastrophe. Entire civilizations of hypothetical aliens could have existed in these consumed galaxies, their homeworlds scattered to the cosmic winds as their galaxies were slowly shredded and digested by our own. Even traveling at maximum universal velocity, the scale of the local group demonstrates that a human lifetime is desperately insufficient for significant exploration. But the local group itself is just a tiny component of something much larger. The local group forms part of the Virgo supercluster, an even larger structure containing thousands of galaxies in an immensely extensive volume. The Virgo supercluster contains at least 100 groups and clusters of galaxies, a massively immense, extensive, gravitationally bound structure. The Virgo supercluster pulls our galaxy at about 890,000 miles per hour toward a region called the Great Attractor, a mysterious gravitational anomaly. This supercluster extends across 110 million light-years in diameter, a dimension that challenges any direct, concrete, intuitive human comprehension. Traveling at light speed, crossing the Virgo supercluster would take 110 million years, a period longer than the existence of dinosaurs. When dinosaurs became extinct 66 million years ago, a photon still wouldn't have completely traversed this gigantic cosmic structure. To put this in perspective, all of dinosaur history, from their earliest emergence in the Triassic period through their dominance and eventual extinction, represents only about 60% of the time light needs to cross our local supercluster. The reign of the dinosaurs, that seemed to dominate Earth for an eternity in geological terms, is insufficient time for light to cross our local cosmic neighborhood. The time from the first Tyrannosaurus rex to the last Triceratops is less than the journey time across the Virgo supercluster. But even the Virgo supercluster is just a component of something larger still. The Laniakea supercluster, an even larger structure containing Virgo, extends across 520 million light-years of totally incomprehensible immense extension. Laniakea contains approximately 100,000 galaxies with total mass equivalent to 100 million billion suns, a colossal, unimaginably massive gravitational concentration. The Milky Way sits on the periphery of Laniakea, not at the center, revealing our insignificant position in large-scale cosmic structure. Crossing Laniakea at light speed would take 520 million years, a period longer than since the emergence of the first terrestrial vertebrate fish. During such a journey, complex multicellular life could evolve from simple organisms to complete advanced technological civilizations and beyond. The entire history of complex life on Earth, from the first multicellular organisms through the Cambrian explosion, the rise of fish, amphibians, reptiles, dinosaurs, mammals, and eventually humans, represents the minimum travel time across our local cosmic superstructure at the universe's speed limit. This is where cosmic structure becomes almost psychologically unbearable to contemplate. We're talking about distances so vast that evolution itself becomes a brief episode in a light-speed journey. The entire story of life on Earth, every extinction event, every evolutionary breakthrough, every species that ever lived, is just a footnote in the time required to cross our local supercluster. But we're still not done. Even Laniakea is just one component of the universe's largest known structures. The Sloan Great Wall, a gigantic galactic filament, extends across 4 billion light-years, one of the largest known structures in the universe. The Sloan Great Wall contains about 10,000 galaxies organized in a filamentary structure, demonstrating that the universe has a texture similar to a spider web. Cosmic filaments are the largest connected structures in the universe, containing trillions of galaxies along billions of light-years of extension. Between these filaments exist gigantic cosmic voids, regions almost completely devoid of matter, where galaxies are extremely rare or totally absent. The Eridanus supervoid extends approximately 1 billion light-years in diameter, a cosmic desert almost completely empty of matter. Crossing a cosmic void at light speed would mean witnessing only darkness for 1 billion years, absolute, unimaginable cosmic loneliness. Imagine traveling for 1 billion years and encountering essentially nothing. No stars, no galaxies, no structure of any kind. Just empty space expanding around you for a period longer than multicellular life has existed on Earth. The distribution of galaxies in the universe resembles a cosmic web, with filaments connecting dense nodes separated by immense extensive voids. Crossing a cosmic void at light speed would mean witnessing only darkness for 1 billion years, absolute, unimaginable cosmic loneliness. This structure formed over 13.8 billion years through gravitational collapse of minuscule primordial ancient quantum fluctuations. Imagine that journey through a cosmic void, 1 billion years of traveling at the universe's speed limit through essentially empty space. When you began that journey, life on Earth would be single-celled organisms floating in primordial oceans. During your billion-year transit through nothingness, complex multicellular life would evolve. The Cambrian explosion would populate the seas with strange creatures. Fish would develop, life would colonize land, forests would grow and die, dinosaurs would rise and fall, mammals would inherit the earth, and humans would eventually appear, develop civilization, and perhaps disappear again. All while you traveled through cosmic emptiness, seeing nothing but the faint glow of the cosmic microwave. Background. The experience would be psychological torture on an incomprehensible scale. Imagine the absolute isolation. No stars, no galaxies, no reference points of any kind. Just you, moving through expanding emptiness for a period longer than complex life has existed on Earth. The human mind simply cannot conceive of such duration or such solitude. You would traverse a region where galaxies are separated by distances so vast that light from one barely reaches the others. The observable universe contains approximately 2 trillion galaxies distributed across 58 billion light-years of total measurable known diameter. Each galaxy is a system of hundreds of billions of stars, totaling about 10^24 stars in the completely entire known observable universe. Let me help you visualize that number. If each star were represented by a grain of sand, we would need billions of planetary beaches completely covered to represent them all. That's not just every beach on Earth. We'd need billions of entire Earth-sized planets, each one completely covered in sand beaches from pole to pole, to represent all the stars in just the observable universe. The number is so large, it becomes meaningless to human comprehension. 10 to the 24th power, that's a 1 followed by 24 zeros. If you wrote out that number with each zero taking up 1 inch of space, the number would stretch over 2 feet long. But even that doesn't capture the magnitude. Each of those stars could have planetary systems, potentially harboring billions of worlds. Traveling at light speed for 13.8 billion years since the Big Bang, you would reach only the current edge of the known observable universe. The observable universe has a radius of 28.9 billion light-years due to continuous accelerated expansion of dynamic space-time itself. This distance is greater than 13.8 billion light-years because space between galaxies expanded while light was traveling to us. It's one of the most mind-bending aspects of cosmology. The light we see from the most distant galaxies began its journey when the universe was much smaller and more compressed. As that light traveled toward us over billions of years, the space it was traveling through expanded, stretching the distance the light needed to cover. Galaxies at the edge of the observable universe are moving away faster than light due to space expansion, without violating special relativity. Space itself can expand faster than light, because no matter is actually moving through space faster than light. The space between objects is increasing. It's like dots drawn on a balloon that's being inflated. The dots aren't moving across the balloon surface faster than any speed limit, but they're getting farther apart because the balloon itself is expanding. The light from these distant galaxies will never reach us, remaining forever beyond our defined, limited physical observational cosmological horizon. It's estimated that 7 trillion galaxies exist beyond the observable universe, a possibly infinite unobservable region we will never see directly. Think about that. 7 trillion galaxies that we will never see, never study, never know anything about, each potentially containing hundreds of billions of stars, trillions of planets, possibly countless civilizations. All of it forever invisible to us, not because our technology isn't advanced enough, but because the fundamental structure of space-time itself prevents that information from ever reaching us. The cosmic event horizon defines the absolute fundamental limit of what we can observe, no matter how long we wait, patiently observing. Even if humanity survived trillions of years, those distant galaxies would remain forever inaccessible due to inexorable, continuous, accelerated expansion. Dark energy, the mysterious force composing 68% of the universe, continuously accelerates cosmic expansion, moving galaxies apart ever more rapidly. In the distant future, isolated galactic clusters will be so far apart they won't see other clusters, with horizons progressively shrinking and always reducing. Future civilizations trillions of years from now might believe only their galaxy exists, their observable universe limited to the gravitationally bound local group. They would look out into space and see only darkness beyond their local galactic neighborhood, never knowing that trillions of other galaxies once filled their night sky. They would have no way to deduce that a vast universe once existed beyond their cosmic horizon. To them, the universe would appear to contain only their local group of galaxies surrounded by infinite empty space. The cosmic microwave background radiation, an echo of the Big Bang, traveled 13.8 billion years to reach us, the oldest testimony of the primordial infant universe. The cosmic microwave background has a temperature of 454.27 degrees, slightly warmer than absolute zero, a thermal remnant from the infant primordial universe. This radiation was emitted only 380,000 years after the Big Bang, when the universe cooled enough to allow neutral atoms to form for the first time. Before this moment, called recombination, the universe was opaque to light, filled with a hot plasma of protons and electrons. When it cooled enough for these particles to combine into hydrogen atoms, the universe suddenly became transparent, releasing the first light to travel freely through space. This light has been traveling toward us ever since, cooling and redshifting as the universe expanded around it. The light we see from the most distant galaxies shows how they appeared when the universe had only 5% of its current present age. Observing the deep cosmos is literally a time machine, with each distance corresponding to a different period of evolutionary cosmic history. When we look at galaxies 10 billion light-years away, we're seeing them as they were when the universe was only 8 billion years old, younger than Earth is today. The finite speed of light transforms telescopes into time machines, allowing us to study galactic evolution across billions of past years. Every observation is an archaeological dig into cosmic history. The deeper we look into space, the further back in time we see. The most distant galaxies appear as they were when they were young, actively forming stars. often colliding and merging with each other in the crowded early universe. A human lifetime of 80 years represents only 0.0579% of the universe's age, an insignificant, temporally negligible, minuscule infinitesimal fraction. At light speed, you would travel 0.86% of the observable universe's diameter during an entire lifetime, a cosmically negligible distance. If the observable universe were reduced to Earth's size, a human lifetime at light speed would cross only 4.3 inches of distance. In spatial and temporal terms, human existence is less than a blink of an eye in the immensely vast and ancient cosmic history. We are temporary arrangements of atoms that briefly achieve consciousness in a universe that existed for nearly 14 billion years before us and will continue for trillions of years after us. Alien civilizations in distant galaxies will never know of our existence, separated by physically impossible, insurmountable abysses of space and time. Radio signals from Earth, traveling at light speed, have reached only 120 light-years, a minuscule bubble in the 100,000 light-year Milky Way. Our oldest transmissions from 1900 are only 125 light-years distant and haven't reached even 0.125% of our galaxy today. Any civilization more than 125 light-years away doesn't know we exist and won't know for millennia, even if they detect our weak signals. Our radio bubble, containing all of human civilization's electromagnetic emissions, represents an impossibly tiny sphere in galactic terms. For galaxies like Andromeda, our signals will take 5 million years to arrive, time during which humanity may cease to exist completely. If a civilization in Andromeda observed Earth today with a powerful telescope, they would see primitive human ancestors making rudimentary stone tools. Think about that cosmic perspective. Right now, if advanced aliens in Andromeda aimed their most powerful telescopes at Earth, they wouldn't see cities, cars, or airplanes. They wouldn't see the pyramids, the Great Wall of China, or any evidence of civilization. They would see early hominids in Africa, barely distinguishable from other primates, perhaps occasionally striking rocks together to make crude tools. To them, Earth would appear to be a planet with no intelligent life. Meanwhile, if we could somehow send a signal to Andromeda today, it would arrive 5 million years from now. By then, human civilization as we know it would likely be unrecognizable, if it existed at all. The message would be like a letter from the Stone Age arriving in a post-human future. Light speed represents simultaneously the absolute maximum limit and a tragically insufficient velocity for true significant cosmic exploration. This fundamental paradox means that even achieving the technologically impossible, we remain imprisoned in a tiny local cosmic bubble with limited geography. There is no conventional technological solution to this problem, as fundamental physics laws prevent superluminal velocities with normal, conventional matter. Special relativity demonstrates mathematically that rest mass grows infinitely as you approach light speed, making acceleration energetically impossible. This isn't just a technological limitation we might someday overcome. It's a fundamental constraint woven into the fabric of space-time itself. As you accelerate any object with mass toward light speed, its relativistic mass increases exponentially, requiring ever-increasing amounts of energy. To reach 99% of light speed requires tremendous energy. To reach 9% requires orders of magnitude more. To reach actual light speed would require infinite energy. The mathematics are unforgiving. Einstein's equations show that as velocity approaches light speed, mass approaches infinity, and thus the energy required for further acceleration also approaches infinity. It's not a matter of building bigger rockets or more efficient engines. It's a fundamental law of the universe that mass cannot reach light speed. Hypothetical projects like solar sails or nuclear propulsion would achieve at most 10 to 20% of light speed, still cosmically insufficient. The Breakthrough Starshot project proposes nanosails accelerated by terrestrial lasers reaching 20% of light speed, traveling to Alpha Centauri. Even at 20% of light speed, these nanosails would take 20 years to reach Proxima Centauri, plus 2 years for signals to return. Think about what that means for exploration. Our very best theoretical technology, pushing the absolute limits of what might be possible, would still require over 2 decades to reach our nearest stellar neighbor. And we're talking about nanosails, tiny wafer-thin spacecraft weighing just grams, carrying minimal instrumentation. No humans, no complex equipment, just gossamer-thin probes racing through the void. These nanosails would be smaller than postage stamps, carrying sensors no bigger than microchips. They couldn't land, couldn't perform detailed exploration, couldn't even slow down when they reached their destination. They would flash past Proxima Centauri at 20% of light speed, taking photographs for perhaps a few hours or days during their flyby, then continue into interstellar space forever. It would be cosmic archaeology, snapshots of alien worlds taken during high-speed flybys. A conventional crewed mission would take centuries, requiring multi-generational ships where crews would be born, live and die during the long journey. Intermediate generations would never see Earth or destination, existing only in spatial vacuum during decades of complete, absolute, total isolation. Imagine being born on a spacecraft between stars. You would know Earth only through stories, videos, and the memories of your parents and grandparents. You would spend your entire life in artificial gravity, breathing recycled air, eating food grown under artificial lights. Your children would know even less about humanity's homeworld. By the time the ship reached its destination, Earth would be a myth, a story told by ancestors who lived in an impossibly different world. The ship would become its own world, its own civilization. Children born in the void would have no reference point for concepts like sky, horizon, or weather. They would know only corridors, airlocks, and the constant hum of life support systems. The psychological adaptation required would be profound. These wouldn't quite be humans as we understand them, but rather a new branch of humanity adapted to life in artificial environments. Hibernation or cryogenics remains science fiction without current technological viability, with apparently insurmountable biological challenges using presently available technology. We've never successfully frozen and revived anything larger than simple organisms. The human brain, with its delicate neural networks, appears particularly vulnerable to ice crystal formation during freezing. Colony ships carrying thousands of people would require perfect closed ecosystems, technology still not mastered after decades of research and testing. The energetic cost of accelerating significant mass to relativistic speeds would exceed centuries of combined accumulated total global energy production. Think about that scale. To accelerate a single ship carrying thousands of people to even 10% of light speed would require more energy than our entire civilization has produced since the Industrial Revolution. We're talking about energies comparable to small stars, concentrations of power that would make nuclear weapons look like firecrackers. Cosmic radiation during prolonged interstellar journeys would cause cumulative biological damage even with heavy shielding, a problem still without adequate definitive solution. Outside Earth's protective magnetosphere, space is filled with high-energy particles that can penetrate most shielding materials. Over decades or centuries, this radiation would cause cancer, genetic damage, and neurological problems. Psychological problems from extreme isolation during decades or centuries are largely unknown and potentially devastating to normal human crews. The psychological challenges might prove even more insurmountable than the physical ones. Humans evolved to live in communities on Earth's surface, under open skies, with natural cycles of day and night. Confining people in a metal tube for centuries, surrounded by the absolute void of space, presents psychological challenges we can barely imagine. Depression, claustrophobia, agoraphobia, existential crisis. How do you maintain human sanity across multiple generations in such an environment? The ship would be a world without horizons, without seasons, without any connection to the natural cycles that shaped human psychology over millions of years of evolution. Even overcoming all technological challenges, galactic exploration would remain limited to the immediate solar neighborhood, with only a few light years realistically achievable. Communication with interstellar colonies would face decades of delay, making coordination or assistance in useful time remotely practically impossible. A colony on Proxima Centauri would have conversations with an 4-year delay between question and answer, making genuine, real, true dialogue impossible. Entire generations would be born and die between a message sent and response received, making communication essentially meaningless for immediate practical purposes. Imagine trying to govern an interstellar civilization with such communication delays. If Earth received a distress signal from Proxima Centauri, help would take over 4 years to arrive, assuming it could travel at light speed, which is impossible for anything substantial. More realistically, any assistance would take decades or centuries to arrive. By then, whatever crisis prompted the distress call would be ancient history. Political meetings between star systems would be impossible. Economic coordination would be meaningless. Cultural exchange would be reduced to sending digital artifacts into the void, hoping someone would receive them decades later. Each colony would be fundamentally alone, forced to be completely self-sufficient from the moment it arrived. Colonies would quickly develop independent cultures, separating from Mother Earth both culturally and politically, probably inevitably, always with certainty. Within a few generations, colonies and Earth would be practically mutually alien civilizations, sharing only distant, remote, ancient common ancestry. Interstellar political unity would be impossible, with each stellar system functioning as a completely autonomous, independent entity by practical necessity. Scientific knowledge would take years to propagate between systems, delaying collective technological development of the geographically fragmented, dispersed human species. Solutions to critical problems would take decades to arrive, frequently becoming irrelevant or obsolete after prolonged, extensive informational travel. If a colony developed a cure for cancer, Earth wouldn't learn about it for years. If Earth discovered a new energy source, the colonies wouldn't know for decades. Each world would be forced to solve problems independently. Humanity would fragment into distinct species eventually, evolving separately under different, unique, specific, particular, planetary, environmental, selective pressures. This fragmentation is inevitable, given the timescales involved. Separated human populations would face different gravitational environments, atmospheric compositions, radiation levels, and perhaps different day-night cycles. Over thousands of years, these populations would begin to diverge genetically and culturally. The humans of Proxima Centauri might eventually become as different from Earth humans as we are from Neanderthals. Different gravity might produce taller, more slender builds. Different atmospheric pressure might affect lung capacity. Different radiation environments might favor genetic mutations we can't predict. After enough time, the colonies might become separate species entirely. The dream of a unified human galactic empire is physically impossible due to light's finite speed, a fundamental barrier of universal natural physics. But what about exotic solutions? What about the theoretical possibilities that science fiction loves to explore? Alcubierre warp drive proposes contracting space ahead and expanding behind the ship, avoiding direct violation of special relativity. This theoretical concept would allow effective superluminal movement without actually accelerating through space, technically circumventing the light speed limit. The ship would remain in a locally stationary spatial bubble while space-time around it moves, analogous to a surfer on an oceanic aquatic wave. But the problems are formidable. It requires negative mass or exotic energy that doesn't exist, quantities beyond all currently available, known, measurable, observable universal energy. Even if exotic energy existed, necessary quantities would equal Jupiter's mass, converted to pure energy, completely, totally, integrally. That's the mass of a planet 11 times wider than Earth, completely converted to energy, according to Einstein's famous equation, E=mc2. The energy requirements are not just enormous, they're galactic in scale. Hawking radiation and quantum effects could destroy any warp structure, making it fundamentally unstable and potentially explosively, lethally self-destructive. An event horizon forming ahead could permanently trap the ship, transforming warp propulsion into an inescapable, fatal, deadly gravitational trap. Particles captured by the bubble would accumulate, releasing devastating explosions upon deceleration, completely, totally, absolutely incinerating the destination without survivors. Even resolving energy issues, we don't know if physical laws really permit stable space-time curvature in this specific proposed manner. Warp propulsion remains purely theoretical speculation, without any experimental evidence or clear path for viable, real, practical implementation. Wormholes are hypothetical tunnels through space-time connecting distant regions, shortcuts through the universe, avoiding long journeys. Einstein and Rosen mathematically demonstrated their theoretical existence in 1935, valid solutions to complex Einsteinian general relativity equations. The fundamental problem, natural wormholes would collapse instantly, closing before any matter could completely traverse the structure. Keeping them open requires exotic matter with negative mass energy, a type of matter never observed and possibly fundamentally physically impossible and inexistent. The quantity of exotic energy necessary could exceed the energy of an entire galaxy concentrated in a minuscule, incredibly dense, compact microscopic point. Even if we built a wormhole, quantum effects near the throat could make traversal instantly, fatally, destructively, certainly lethally dangerous. Think about those energy requirements for a moment. We're talking about harnessing more energy than 200 billion stars produce over their entire lifetimes, then concentrating that energy into a space smaller than an atom. It's not just technologically challenging, it approaches the realm of physical impossibility. Quantum fluctuations could unpredictably and catastrophically destabilize the structure, collapsing it during traversal and permanently, tragically, eternally trapping travelers. Wormholes could theoretically be time machines, raising causal paradoxes that violate fundamental principles of established, known, temporal physics. Stephen Hawking's chronology protection principle suggests that nature conspires to prevent time travel, possibly equally prohibiting traversable wormholes. So far, no observational evidence suggests the existence of natural or artificial wormholes in the totally measurable, observable known universe. The physics laws seem to conspire to prevent rapid interstellar travel, establishing apparently insurmountable fundamental limits with known conventional technology. This isn't merely a matter of insufficient current technology, but potentially fundamental physical impossibility of the immutable universal natural laws themselves. The speed of light isn't arbitrary. It emerges from the fundamental structure of space-time as described by rigorous Einsteinian special relativity. Changing this speed would require altering the fundamental constants of the universe, potentially totally destroying the entire structure of known physical reality. The principle of causality requires that causes temporally precede effects. Superluminal travel would allow causal violations, creating absurd, impossible logical paradoxes. Information traveling faster than light would permit communication with one's own past, contradicting the universal, known, always observed linear temporal experience. Imagine the chaos if you could send information to your past self. You could prevent your own birth, create paradoxes where effects precede their causes, or accumulate knowledge from futures that might never happen. The universe seems specifically designed to prevent such logical contradictions. The universe appears designed to prevent such violations, suggesting that light speed limitation is protection against destructive fundamental logical inconsistencies. Theories of quantum gravity may modify relativity at extreme scales, but are unlikely to permit viable, real, practical macroscopic superluminal travel. Hopes of discovering completely new physics allowing FTL are analogous to expecting that basic mathematics is fundamentally completely inverted and wrong. Even civilizations millions of years more advanced would face the same physical limits. Universal natural laws apply equally universally, always, everywhere. This is a sobering realization. We often imagine that sufficiently advanced civilizations might transcend physical limitations, but the laws of physics aren't suggestions. They're ironclad rules that govern all matter and energy in the universe. A civilization 1,000,000 years ahead of us would still be bound by the same speed limit, still face the same energy requirements, still confront the same fundamental barriers. The universe wasn't designed to be completely explorable by a single species during the brief, fugacious, limited time of civilizational existence. Our cosmic insignificance doesn't diminish the value or meaning of human existence. It merely contextualizes our position in the larger, broad universal scheme. The unattainable vastness of the cosmos invites contemplation and admiration, not despair or unnecessarily exaggerated, destructively negative, pessimistic, defeatist resignation. Physical limitations define the conditions for our existence, just as gravity allows planets to form while securely, firmly binding us to planetary surfaces. Think of these limitations not as cosmic cruelty, but as the very conditions that make life possible. The same physics that prevents us from easily traveling between stars also prevents stars from easily colliding with each other, creating the stable stellar neighborhoods where planets can orbit peacefully for billions of years. The same space-time structure that limits our speed also allows matter to exist in stable forms, permitting the chemistry that builds complex molecules and living organisms. The impossibility of galactic exploration doesn't make life meaningless. Meaning emerges from local experiences, not from impossible, unattainable cosmic conquests. Civilizations can flourish and create profound meaning within a single stellar system, not needing a galactic empire for existential importance or purpose. Focusing on the possible instead of the impossible, in-depth exploration of the solar system offers centuries of rich, varied, productive, sustainable discoveries and development. The Moon, Mars, asteroids, and the moons of Jupiter and Saturn are achievable with current or near-future technology, representing a genuine, viable, practicable, real frontier. Consider what we could accomplish within our own solar system over the next few centuries. We could establish permanent bases on the Moon and Mars, mine asteroids for rare metals, explore the subsurface oceans of Europa and Enceladus, study the atmospheric dynamics of gas giants, and perhaps discover microbial life in dozens of different environments. Each of these worlds represents entire new frontiers for human exploration and development. Intelligent robotic exploration can extend observational reach beyond human capabilities. Probes like the Voyagers have already crossed the historic heliosheath frontier. Advanced space telescopes like the James Webb allow us to observe the deep universe, exploring without the need for currently technologically impossible personal physical travel. We don't need to physically visit distant galaxies to study them. Our telescopes are time machines, showing us how the universe looked billions of years ago. We can analyze the chemical composition of exoplanet atmospheres, study the formation of the first stars, and observe the cosmic web's structure, all from our solar system. Civilizational success doesn't require galactic expansion, but rather sustainability, knowledge, art, culture, and broad, inclusive, generalized, universal conscious well-being. Mature civilizations can dedicate themselves to profound understanding, not merely spatially limited, geographically, physically, material, territorial, superficial, expansionist exploration. What defines a successful civilization? Is it the number of stars it controls or the depth of its understanding? Is it territorial expansion or the flourishing of consciousness and culture? Perhaps our cosmic isolation forces us to focus on what truly matters, not conquest, but comprehension, not expansion, but enlightenment. Communication with extraterrestrial intelligence, if it exists, may occur via electromagnetic signals over decades or centuries of patient expected waiting. Projects like SETI continue hopefully listening to the cosmos, searching for signals from other civilizations, facing the same identical, universal, fundamental physical limits. The discovery of microbial life on Mars or icy moons would be profoundly transformative, demonstrating that life emerges easily under appropriate, adequate conditions. Astrobiology studies potential life in the solar system, an achievable objective with robotic missions in the upcoming, imminent, approaching future decades. Understanding the origin and nature of life may be more significant than merely finding it in physically impossible, remote, inaccessible, unreachable, distant locations. Preservation of Earth's biosphere becomes a moral imperative, perhaps the only accessible complex life during all known possible human civilizational existence. The potential rarity of intelligent life in the observable universe increases the importance of preserving and valuing consciousness existing here, presently, currently, now. Cosmic responsibility emerges from understanding. We are potentially unique guardians of consciousness in a vast, surrounding, adjacent, nearby local galactic region. If intelligent life is rare, and the silence of the cosmos suggests it might be, then we bear enormous responsibility. We might be the only thinking beings within thousands of light years. Every human mind, every work of art, every scientific discovery, every moment of love or creativity might be cosmically precious simply because consciousness capable of appreciating the universe's beauty is so rare. This perspective transforms our relationship with existence itself. We're not failed cosmic explorers, frustrated by our limitations. We're successful cosmic observers, privileged witnesses to the universe's grandeur. We can see across billions of light years, peer back through billions of years of cosmic history, and understand the fundamental laws that govern reality, from subatomic particles to galactic superclusters. The speed of light isn't our prison, it's our teacher. It shows us the true scale of the universe, humbles our cosmic ambitions, and forces us to find meaning not in conquest, but in contemplation. We remain forever local, but our minds can encompass the cosmos. Cosmic distances reveal that each human encounter is statistically improbable, almost miraculous, considering the total, general, complete, absolute, integral, universal vastness. The atoms in our bodies were forged in stars billions of years ago. We are literally organized stellar dust, contemplating our ancestral cosmic origin. Think about that for a moment. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in the nuclear furnaces of ancient stars. Carbon, oxygen, and nitrogen essential to life were created in stellar nuclear furnaces, scattered by violent, explosive, destructive, massive supernovas. Every element heavier than hydrogen and helium in your body required the death of a star to create it. Each human being contains approximately 7 octillion atoms, each one with a cosmic history spanning billions of years through multiple stellar generations. That's 7 followed by 27 zeros, a number so vast it's almost meaningless to human comprehension. But each of those atoms has traveled through space for eons, been part of gas clouds, incorporated into previous stars, expelled in stellar winds or supernova explosions, drifted through the interstellar medium, and eventually found its way into the solar nebula that formed our sun and planets. You are not separate from the cosmos. You are the cosmos, temporarily arranged into a thinking, feeling pattern. The universe has spent 8 billion years creating the conditions for your existence, forging the elements in your body, assembling the molecules of DNA that define your biology, and creating the planet where you can contemplate your own cosmic nature. The rarity of adequate conditions for complex life suggests that conscious existence may be an exceptional, extraordinary, rare, precious, invaluable, unique phenomenon. The anthropic principle indicates that the universe must have properties allowing observers, or we wouldn't be here to philosophically, profoundly, reflexively, introspectively question it. Fine-tuning of fundamental physical constants permitted the emergence of complexity, galaxies, stars, planets, and finally, intelligent thinking, rational, conscious life. Small variations in these constants would make the universe sterile, without stars or heavy elements necessary for sophisticated, elaborated, complex carbon-based biology. Consider how precisely calibrated our universe appears to be for the existence of complexity. If the strong nuclear force were slightly weaker, atomic nuclei couldn't form. If it were slightly stronger, hydrogen would be unstable. If gravity were much stronger, stars would burn out quickly before life could evolve. If it were much weaker, stars and galaxies might never have formed at all. Whether it's extraordinary coincidence or an infinite multiverse, our existence requires precisely specific, particular, exact, rigorously calibrated, finely determined conditions. Regardless of the ultimate explanation, the fact remains, we are here, capable of contemplating the universe and our minuscule position within it, immensely vastly. Ancient civilizations built pyramids, temples, and monuments, hoping for immortality through stone, and inherited past generationally transmitted cultural memory. On the cosmic scale, even these structures are ephemeral. They will disappear when the sun becomes a red giant in 5 billion distant remote future years. Think about the irony. The pyramids of Egypt have stood for nearly 5,000 years, seeming eternal to human perception. Yet in cosmic terms, they're temporary sandcastles on a beach. Even if they survived until the sun's death, which they won't, that entire span represents just a tiny fraction of the universe's age. Human legacy may not be physical, but informational. Knowledge encoded in signals propagating at light speed through the expansive cosmos. Voyager 1 and 2 carry golden records with sounds and images from Earth. Messages in bottles launched into the infinite, vastly immeasurable cosmic ocean. These probes will exist for billions of years after humanity disappears, silent monuments to our brief, temporally limited ephemeral curiosity. In 40,000 years, Voyager 1 will pass near star AC Plus 79 3888 at 1.6 light-years distance, continuing its eternal, solitary, silent, perpetual journey. If extraterrestrial civilization finds the Voyagers, they will learn about the species that built them millennia ago, technological fossils from a perhaps vanished extinct civilization. Our heritage may be knowledge transmitted through future terrestrial generations, not totally physically unfeasible, logistically impractical, impossible galactic conquest. Each generation adds to the sum of human understanding, building upon foundations established by ancestors over progressively sequentially accumulated millennia. This intellectual and cultural legacy may be more enduring than any physical structure, persisting while there are minds to consciously preserve it. Consider what we've accomplished in just the past few centuries. We've discovered the age and size of the universe, understood stellar evolution, decoded the genetic basis of life, developed quantum mechanics and relativity, and begun to understand consciousness itself. Each generation stands on the shoulders of giants, seeing farther into the cosmic mystery than any previous generation could imagine. Limitations define the human condition, shaping experiences and meanings in profoundly fundamental, essential, central, nuclear, primordial, basic, foundational, radical ways. Immortality and omnipresence would eliminate urgency, purpose, and meaning that emerge from limited, restricted, circumscribed, confined, delimited existential, temporal, spatial finitude. The impossibility of exploring everything makes each discovery more precious, each astronomical observation a privilege that is appreciated, valued, esteemed, recognized, celebrated. We cannot visit distant stars, but we can study them through light that patiently traveled billions of years to our terrestrial telescopes. This connection through light is a temporal spatial bridge, linking us to distant events in space-time in profoundly significant, poetically beautiful ways. The cosmic scale emphasizes the preciousness of consciousness, the capacity to understand the universe, even while being completely, totally, integrally, physically unable to access it. When you look up at the night sky, you're not just seeing distant suns. You're witnessing the history of the universe. The light from each star began its journey years, decades, centuries, or millennia ago. You're seeing Sirius as it was 6 years ago, Vega as it was 25 years ago, and the Andromeda galaxy as it was 5 million years ago. Your eyes are time machines, and every photon that enters them has traveled across the cosmic dark to tell you a story about when and where it began its journey. We are an arrangement of atoms becoming self-aware, the universe contemplating itself through statistically rare, sophisticated, complex, emergent structures. This cosmic self-consciousness is perhaps rarer than we imagine, making each mind an extraordinarily improbable, precious, invaluable, unique, singular, exceptional phenomenon. Value doesn't reside in conquering the cosmos, but in understanding it, appreciating it, and connecting with it intellectually and emotionally, profoundly, intensely, significantly. The inaccessible vastness of the universe inspires humility and admiration. Emotions essential for wisdom and mature, balanced, healthy, realistic, pragmatic, existential perspective. All the stars we see share common origin in the Big Bang 13.8 billion years ago. United by shared common ancestral cosmic history, physical distances don't diminish ontological connection. All parts of the same evolutionary dynamic, systematically, holistically, universally, globally interconnected universe. Physical laws are universal. The same equations govern atoms here and in galaxies billions of light-years away in physical, geographical, spatial distance. This uniformity suggests a fundamentally interconnected universe, despite vast, apparent, superficial, empirically measurable, detectable, scientifically observed spatial separation. The cosmic microwave background radiation connects all regions of the observable universe, a universal thermal bath at 454, 27 degrees permeating all space uniformly consistently. Quantum fluctuations in the primordial, primitive, initial, nascent, emergent infant universe generated seeds of all current, present, modern, contemporary existing structures. Those ancient quantum fluctuations, occurring in the first fraction of a second after the Big Bang, determined where galaxies would form, where stars would ignite, where planets would coalesce, and ultimately where life would emerge. The pattern of slight density variations that would eventually become galaxy clusters and cosmic voids was established when the universe was smaller than a grapefruit and hotter than the core of any star. Every structure in the universe today, from the smallest asteroids to the largest superclusters, traces its existence back to those primordial quantum fluctuations. The cosmic web that stretches across billions of light years, the spiral arms of galaxies, the location of our solar system, and ultimately the existence of Earth itself, all stem from quantum uncertainty in the universe's first moments. We are the universe becoming aware of itself, temporary patterns of complexity that emerged from cosmic evolution to witness and comprehend the very processes that created us. Galaxies separated by billions of light-years descend from adjacent fluctuations in the initial, primeval, hot, dense, uniform, homogeneous, isotropic, primordial plasma. This common ancestry unites the cosmos despite current present modern isolation, a dispersed universal family, but fundamentally ontologically related, essentially connected. Even unable to reach distant regions, we participate in a shared, collective, unified, integrated, cohesive, harmonious, consistent, universal cosmic narrative. Our curiosity about the distant universe reflects a universal tendency toward complexity, consciousness, and understanding emerging over evolutionary cosmic eras. Think about the profound implications of this cosmic genealogy. Every galaxy we see through our telescopes, from the nearest dwarf galaxies to the most distant quasars, originated from quantum fluctuations that were once neighbors in a space smaller than a subatomic particle. What are now cosmic distances of billions of light-years were once adjacent ripples in the fabric of space-time itself. The Andromeda galaxy and the Milky Way, separated by 5 million light-years of void, began as neighboring perturbations in the primordial quantum foam. Current physics may not be the final word. Future scientific revolutions could reveal completely unexpected, surprising, transformative, revolutionary, paradigmatic phenomena. However, reasonable expectation is that fundamental limits will persist. Revolutions modify, but rarely completely, totally, absolutely eliminate established, validated, universal, natural restrictions. The history of science shows that ancient theories remain valid in appropriate regimes. Relativity incorporates Newtonian physics rather than completely, totally, absolutely eliminating it. The discovery of black holes evaporating via Hawking radiation or dark energy, accelerating expansion, demonstrates that surprises still exist to reveal and discover. Consider how scientific revolutions typically unfold. When Einstein developed relativity, he didn't prove Newton wrong. He showed that Newton's laws were approximations that work perfectly well at everyday speeds and scales. Similarly, quantum mechanics didn't eliminate classical physics. It revealed the deeper reality underlying classical behavior. Even if future discoveries reveal new physics beyond our current understanding, the fundamental limitations we've discussed, The energy requirements for accelerating mass, the causal structure of space-time, the finite speed of information transfer are likely to persist in some form. The coming decades may bring advances in quantum gravity, unifying relativity and quantum mechanics, and possibly modifying our understanding of fundamental basic space-time. String theory, loop quantum gravity, or other approaches may reveal the structure of space-time at minuscule infinitesimal microscopic Planck scales. These theories could in principle modify our understanding of causality and light speed, but are unlikely to permit practical macroscopic superluminal travel. Advanced civilizations may develop technologies beyond our imagination, but would still be limited by absolute, omnipresent, immutable, universal, fundamental physical laws. Even if consciousness could be digitized, uploaded to quantum computers, or transferred to exotic substrates, the fundamental problems remain. A digital mind traveling to Alpha Centauri would still need to transmit its information at light speed, taking over 4 years to make the journey. A quantum consciousness might process information differently, but it would still be bound by the same relativistic constraints that limit matter and energy. Speculation about post-biological digital intelligences or transferred consciousnesses doesn't solve the fundamental problem of physically imposed, inevitable limiting distances and velocities. Dreams of technological transcendence must recognize reality. The physical universe imposes real limits, not merely technological, but fundamentally ontologically deeply rooted ones. Light speed is slow only when compared to cosmic immensity, a perspective that emerges from understanding true, authentic, universal scale. For everyday terrestrial human phenomena, light speed remains incomprehensibly fast, crossing the planet in imperceptible, minuscule fractions of seconds. Human limitation isn't a defect, but a characteristic of our finite nature, defining the conditions under which conscious life emerged, evolved, and prospered. Acceptance of physical limitations doesn't mean resignation, but mature realism tempered by profound understanding of immutable universal governing natural laws. This acceptance represents wisdom, not defeat. We are not cosmic failures because we cannot travel to distant galaxies. We are cosmic successes because we can understand why such travel is impossible. Our limitations define us as much as our capabilities. The same physics that prevents us from easily exploring the cosmos also makes stable atoms possible, allows stars to shine steadily for billions of years, and creates the conditions under which complexity and consciousness can emerge. We can find meaning, purpose, and fulfillment within an achievable, accessible, viable domain, not needing the impossible to validate intelligent, conscious existence. The capacity to understand the universe, even without being able to explore it completely, is itself extraordinary, improbable, and precious, extremely rare, singular, unique, exceptional. Consider what an achievement human understanding represents. In just a few centuries, we've progressed from believing Earth was the center of creation to comprehending the age, size, and structure of the observable universe. We've discovered that space and time are interwoven, that matter and energy are equivalent, that quantum mechanics governs the subatomic realm, and that the universe itself is expanding. We've detected gravitational waves, imaged black holes, and identified thousands of exoplanets. No previous generation in human history has known as much about the cosmos as we do today. We are conscious witnesses of the cosmos, a privileged position that transcends physical limitations through abstract, conceptual, theoretical, mathematical, philosophical, intellectual understanding. Perhaps the final lesson is humility. We are not destined to conquer the cosmos, but to appreciate it, understand it, and find our place within it respectfully. The inaccessible vastness of the universe doesn't make life meaningless, but emphasizes the preciousness of each conscious moment experienced, lived, and genuinely authentically felt. Every moment of awareness, every flash of understanding, every experience of beauty or wonder becomes infinitely valuable when viewed against the cosmic backdrop. When you watch a sunset, you're witnessing the light from a nuclear furnace 93 million miles away, filtered through an atmosphere that formed over billions of years on a planet that coalesced from stellar debris. When you feel love, you're experiencing emotions that evolved over millions of years in brains made of atoms forged in ancient stars. When you contemplate these words, you're participating in the universe's attempt to understand itself through conscious beings that emerged from its own evolutionary processes. The profound irony of our situation is that our very limitations make us more remarkable, not less. A being that could travel instantly anywhere in the universe might never develop the deep appreciation for distance and time that drives human curiosity. An immortal consciousness might never feel the urgency that motivates scientific discovery. Our constraints have shaped us into creatures capable of transcending those constraints intellectually, even if we cannot transcend them physically. We live in the brief window between the emergence of intelligence and the heat death of the universe. We exist in the tiny, habitable zone around an ordinary star in an unremarkable galaxy during the cosmic epoch when stars still shine and planets can support life. Yet from this modest vantage point, we have managed to see across billions of light years and back through billions of years to understand our cosmic context. The universe took 13.8 billion years to create creatures capable of understanding that 13.8 billion years of cosmic evolution created them. That may be the most remarkable fact of all. In the end, light speed is not an obstacle but a reminder. We are part of a vastly magnificent universe, connected through light traveling patiently through the cosmic intergalactic interstellar universal void since primordial original temporal beginnings. Let's step back and contemplate what this journey has revealed. A human being traveling at light speed would complete 7 full trips around Earth in just 1 second. Earth's equatorial circumference of approximately 24,901 miles would be traversed almost 7.5 times in the blink of an eye, the closest and most familiar scale we can imagine on our planet. Reaching the moon would take 1.28 seconds one way. That average distance of 238,855 miles, which during the Apollo missions generated that famous delay of approximately 2.6 seconds in conversations between astronauts and Houston, our closest neighbor in the cosmos. Getting to the sun would take 8 minutes and 20 seconds. That's exactly 92,955,807 miles, one precise astronomical unit. The sunlight illuminating your face right now left the sun exactly that long ago. If the sun suddenly went dark, you would still have 8 minutes of light and warmth before noticing anything had changed. To reach Neptune, the most distant officially recognized planet, would require about 4 hours and 10 minutes when the planets are favorably aligned. That's approximately 2.8 billion miles, more than 30 times the Earth-Sun distance, showing how immense the solar system already is, even in its inner regions. Crossing to the heliopause, the boundary where solar wind meets the interstellar medium and true interstellar space begins, would take approximately 16 hours and 40 minutes. That's roughly 11 to 12 billion miles. Voyager 1 took 35 years to get there. At light speed, you would do it in less than a day. Reaching the nearest star, Proxima Centauri, would demand 4 years and 3 months of continuous travel. That's 24 light years, approximately 24.9 trillion miles. Even humanity's fastest probe would take tens of thousands of years to cover this minuscule distance on the galactic scale. Reaching the center of the Milky Way, where Sagittarius A resides, would take 26,000 years. When you departed, humanity was still living through the last ice age, hunting woolly mammoths and drawing on cave walls. The supermassive central black hole of our galaxy sits 26,000 light-years away. Traveling to the Andromeda galaxy, M31, our giant spiral neighbor would consume 5 million years. When you departed, our most primitive ancestors were just beginning to make the first napped stone tools. Andromeda lies 5 million light-years away. Crossing the Laniakea supercluster, the gigantic gravitational structure where the Milky Way is located, would require 520 million years at light speed. When you departed, the first vertebrates were just beginning to conquer dry land, one of the largest known concentrations of matter in the observable universe. The current diameter of the observable universe is approximately 58 billion light-years, even traveling continuously at light speed since the Big Bang 13. 8 billion years ago, you would only now reach the edge of what we can, in principle, observe, because the space between galaxies expanded while light was traveling, stretching distances to about 28.9 billion light-years in each direction. These distances aren't just large numbers. They represent the fundamental architecture of reality, the stage upon which the drama of cosmic evolution has played out. They tell us that the universe is not designed for rapid exploration by biological creatures like ourselves. Instead, it appears designed for patience, for contemplation, for the slow accumulation of understanding across generations. The light speed limit isn't cosmic cruelty, it's cosmic wisdom. It ensures that causality remains intact, that effects follow causes, that the logical structure of reality remains consistent. It prevents paradoxes that would unravel the fabric of existence itself. The same constraint that limits our physical exploration enables the stable universe in which consciousness can emerge and flourish. We began this journey asking why light is impossibly slow. Now we understand light isn't slow at all. The universe is impossibly vast, and that vastness, rather than diminishing us, elevates us. We are the universe's way of knowing itself, temporary arrangements of matter and energy that have achieved the remarkable ability to contemplate the very cosmos that created us. If you're still awake, it's because the content was really good. So, take a moment, leave a like and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.